Hi everyone, my name is Mats Kainberg and I'm working at ABB Distribution Solution in Vaasa, Finland as a trainer for our protection relays and protection relay applications. The topic for this webinar is line differential protection. So I will start with an introduction with general information about line differential protection and its advantages. Then I will talk about the protection communication, what communication media options we can choose between, and compatibility. Next, we have operation principle, where I will explain the basics for line differential protection and which other functions in the relay it cooperates with. Then we take a closer look at the line differential operation characteristic and how to define its settings. Then I will show you different application examples where line differential protection can be used. And then finally, before we end up with a summary, I will bring up a couple of things about CT recommendation and where to find more information on that topic. So line differential protection, it consists of two relays. We say that we have a relay, a local relay and a remote relay. And between these relays, we have a communication channel. And both of these relays measures three-phase current. And we say that we have a phase segregated two-end line differential protection. And this means that we are calculating the differential current in each phase separately. And two-end line differential protection means that it's two-ended. And since line differential protection only operates for faults inside the protected zone, we say also it's absolutely selective. We can use line differential for cables or overhead lines, and we can also include in-zone transformers inside the protected zone. And the communication channel here between the local and remote line differential relay, it can either be of optical fiber or galvanic pilot wire. We have also backup protection available in these relays in case the communication fails. And our line differential relay supports as well combi sensors and as well as CTs. And this protection is available from our product portfolio in both RED 615 and REX 640. So what are the advantages with line differential protection? So already mentioned, it's a very selective protection, and it also provides a very sensitive protection because we are not dependent on the load current, since we are looking at the differential current between the two relays. And what we can include here is both a line and a line including a power transformer. It can be used also in any network topology, and it doesn't matter what type of network earthing we have. And there's no need to do any time coordination like for overcurrent protection, since we are only looking at the differential current, and that means also that when we are operating for faults only inside the protected zone, we can, in most cases, use operate time, which is at minimum 45 milliseconds for this protection. And only three-phase current is required. No need to use voltage measurement like you need to use for directional overcurrent protection. On the disadvantages side, we have a couple of things, and the first one is that we cannot use line differential protection if we have a line with two or more branches. And we also always rely on the communication between the line differential relay. So we just have to have a communication. And as mentioned already, it's either optical fiber or a galvanic pilot wire, which we can support. And if you have a very long line that you want to protect, it might need that be that the attenuation in the fiber can exceed the allowed limit. So this means that it's not possible to use line differential protection in that case. So what fault types can line differential protection detect? Well, first of all, we can detect face-to-face faults inside the protected zone in any type of network. Earth faults can be detected in solidly and resistance earthed networks, and also in networks with isolated neutral. If we have a compensated network, we're not able to detect the earth fault with line differential protection. So for this, we need to use a separate earth fault protection function. Okay, so let's then have a look at the protection communication. So the protection communication, it's as mentioned, it's either an optical fiber or a galvanic connection. If it's a fiber, we support two different types of fiber. We support multi-mode fiber or single-mode fiber. If you have multi-mode fiber here between the line differential relays, the maximum length of the fiber can be 2 kilometers. If you use single-mode fiber, it says here now that it can be up to 20 kilometers. But all this depends on the total attenuation in the fiber. So it might not be that we can have a line up to 20 kilometers here. What you always need to do is measure the fiber attenuation, and it shouldn't exceed 8 decibel. And this is now for the RED 615 relay. And one other thing I would like to point out when measuring the fiber is that normally the fiber between the two substations is an underground fiber cable. And in each end of the fiber, you have a patch box from where you then have a patch cable to your line differential relay. This you have in both ends. And when you measure the fiber, it should be measured so it includes the patch fiber in both relays. This way we can include also the connectors here in the patch box, because they usually bring about a half decibel of attenuation. If we then look at the REX 640 relay, there we also support multi-mode and single mode fibers. And here's the same thing. If you have multi-mode, you can have a maximum 2 kilometer fiber. If you have single mode, then you can choose between two different SFP modules that you can plug in your relay. And we have one that supports up to 20 kilometers, or let's say in this case attenuation up to 13 decibels. Then we have a long range which can handle a fiber which have an attenuation up to 26 decibel. So here we can have a fiber that can be up to 50 kilometers long. But as mentioned, it all depends on the attenuation in the total, in the whole fiber. The second option is to use a galvanic twisted pair cable as the communication media. And for this, we have a dedicated pilot wire modem available. And by utilizing this pilot wire modem, we can connect to the galvanic twisted pair cable, and also via optical fiber then to our line differential relay. So with this kind of solution, we can have distances up to 8 kilometers. But it again all depends on the quality of the twisted pair cable. It can be longer and it can be shorter. And these modems, they comes in pair when you order them. So you always have a pair of a master and a follower modem. These modems also show here with some LEDs the quality of service, so you can see that how good is the communication quality between the modems. Then a couple of words about the compatibility between RED 615 and REX 640. So what you can see here in this picture, it's possible to use both RED 615 and RED 640, REX 640 when protecting a line. So you can have REX in one end and RED in the other end of the line. What is important to note here that the RED 615 must have a software version later than 5.0 FP1. This applies also when using the RPV 600 modems for the pilot wire approach. So there is also possible to have REX communicating with RED relay. So let's then have a closer look at the operation principle for line differential protection. So it works in this way that both relays are measuring the current in each end of the line. And this current measurement is then sent out on the communication link to the other relay. And since the other relay is also measuring its own current, it can calculate the differential current, the difference between the received and the measured current. So if the received and the measured current is same, well, then everything is normal and we don't have any fault on the line inside the protected zone. But if we have a fault inside the protected zone, the measured current and the received current from the other relay will not be the same. So we will then have a differential current. And This differential current is then compared to a stabilized characteristic that we are using. And if the differential current is higher than the characteristic, the differential protection will operate. And differential protection will always operate the circuit breaker in both ends of the line. In case we have a fault downstreams, the fault current will be seen by both relays. So this means that we will not have any differential current, and the differential protection will not operate. But instead, the protection device protecting, for example, this feeder then will clear the fault instead. So let's then have a look at different other functions inside the relay that is cooperating with the line differential protection. So the first one I would like to show you here is the protection, communication, supervision. So this function, it continuously checks that the communication between the relays is okay. So in case there's a failure in the communication, line differential protection will immediately be blocked, so it will not operate. And at the same time, the relay will indicate a communication fault. And also at the same time, it is possible to activate additional overcurrent protection function, which serves then as backup protection to line differential protection. This is how it is built in the standard configuration of RED 615. But so it's since these are freely programmable relays, you can choose what will exactly happen when there's a problem with the communication. Then we have a binary signal transfer function. And with this function, we are able to send and receive 8 freely configurable binary signals between the line differential relays. So what we are doing is that we are taking advantage of the protection communication link between the relays. So what can we do with this with these binary signals? Well, like in this example here, this relay is measuring the earthing switch position and also the circuit breaker position. And this information is then sent over the protection communication link to the other relay. And since this end of the line is now earthed, we can bring that information to the other relay and create an interlocking logic. So we cannot close the circuit breaker in this end of the line. Other things we can do with the binary signals is that we can send in the tripping signals to the other relay, so we can operate the circuit breaker in both ends of the lines. We can send blocking signals when one relay is detecting inrush current, or if there's a current circuit failure. We can use them for remote alarming and also for different cross-blocking protection schemes. So there's a lot of different things you can use these binary signals for. Then we have the current circuit supervision function. And this function, it is continuously monitoring the CT secondary circuit in case you have a broken conductor between the CTs and the relay. Because if that happens, it means that the relay will measure wrong current, and that will result in that line differential protection will operate. So how this works is that the function is calculating the sum of all the three-phase currents and then comparing it to a reference current. Now this reference current, it is normally the earth fault current measurement coming from a cable core CT. I will show you an example picture of this in the next slide. And when this function detects a fault in the secondary circuit, what we can do then is block the line differential protection to prevent unwanted operation. And this is, as I said, it's you can choose this, of course, if you want to operate the line differential protection due that you have a fault in the current circuit, or if you just want to block it. So you can choose this. So here is one connection diagram example of the current circuit supervision. So here you can see that we are measuring three-phase current, and here we have a core balance CT for earth fault current measurement, which is then connected to the earth fault current input on the relay. And this same input is used as the reference current. So for the current circuit supervision in a normal situation, when it's calculating the sum of the three-phase current, it should be 0, and also the earth fault current, the reference current here in this case, will also be 0. So that is in a normal situation. So, but in case one phase is missing, the sum of the three phase will not be 0 anymore. So the function will measure a differential current and then issue an alarm and block or operate or whatever you have programmed the relay to do. What is important when using this function is that the reference current needs to come from a separate core. It's not possible to do like in this other picture where we are connecting the sum current from all three-phase currents to the reference input. This is not possible, so we will not be able to detect any secondary current circuit failure here. So the reference current measurement, it needs to come from either a separate core from the three-phase current transformers, or then from a core balanced CT. It's also possible to use the measurement core in the CTs. Then in case we have in-zone transformer here, or let's say a tapped load inside the protected zone. So looking now at this part of the network here. So when we energize this part of the line, it means that this tapped load transformer, it will you will have an inrush current flowing to this transformer, and this inrush current is only seen in this relay but not in the other one. So that means that the inrush current will be purely differential current. So what we can do here is we can activate the inrush current detection in the relay, and over binary signal transfer send that blocking information to the other relay. So we are not operating line differential protection when energizing this line. If we then connect the next part of the network, we have here an in-zone power transformer. So now the inrush current will then be seen by both of these relays. So there's no problem then with that these two relays will see a inrush current and operate the line differential based on that, because the current will be the same. But again, in this case, this relay will see the inrush current, but not the other one. So in this case, it's also important to detect the inrush situation and send a blocking signal to the other relay. Since we have here in-zone power transformer, we might also need to think about that if we need to also block overcurrent protection in these relays here. So then we move on, looking more closely at the line differential characteristic and its settings. So the line differential characteristic, it has this kind of a stabilized characteristic. And in this diagram, we have here on the y-axis, we have the differential current, the calculated differential current. And here on the x-axis, we have the bias current. So when we have a fault here inside the protected zone, we can expect that the differential current will be high. So if we put that current information into this diagram, we can say that the differential current will be roughly about here. So we will have a high differential current and a low bias current. If the fault is downstreams, it then means that we will have a high load current, which is then also seen as a high bias current, but the differential current will be low. There will, however, be some differential current due to measuring error in the CTs, which will increase the higher current they will measure. And also we might have some partly saturated CTs, which also will result in a measured differential current. But the important here is that for outside faults, the currents in this diagram should be below the characteristic here. So when thinking about the stabilized characteristic, there's quite many things that we need to consider here. And main things are that first of all, we need to look at the application in general. Are we using CTs or are we using sensors for measuring the current? Do we have a in-zone power transformer? Do we have a tapped load? In case of an underground cable, there might be considerably high charging currents. So we might need to also look at calculate at how big is the charging currents. And when we have calculated the characteristic, we will use the same settings for the characteristics in both units. If we have an in-zone power transformer, we also need to look at what kind of windings we have in the power transformer. So we need to compensate for the winding types and clock numbers. So we need to give the protection, the information that, okay, do we have a star or a delta winding? And in case of tapped load or an in-zone transformer, we also need to activate the inrush current blocking and also give a proper setting for the inrush current level. In case we have different CT ratios in local and remote end, we need to compensate for this with help of the CT ratio correction parameter. And we also need to provide the protection function, the information that, okay, that with which polarity we have connected our CTs to the protection relays. And this is set then with the CT connection type. Looking then more closely at the differential characteristic settings. So we have quite many settings here that we can adjust the characteristic with. We have low operate value. We can adjust the end section 1. We can adjust the slope section 2, how steep the slope is, when the end section 2 will start, and also how steep the slope section 3 will be. We also have a high operate value available here. And the high operate value, it will clear the fault without any operation delay, and it will not consider any inrush blocking. So let's then start by looking at these different settings that forms this characteristic, and what we should consider when we are calculating the settings. So for the low operate value, here we can define the basic sensitivity of the protection. So here we include relay measuring error, and in case we have a tapped load, we must include also the load current going to the tapped load, since it will be seen as pure differential current. Also, we need to include if we have a charging currents, and in case of our in-zone power transformer, we need to include the no load losses and a margin. For the end section 1, it defines when slope section 2 will start. So it means that at which load current can we tolerate more differential current. So the higher the load current, the more differential current can we tolerate. And this again depends on the application. So if we only have a line that we are protecting, we can use 100% IR. And the IR here means it's the same as the nominal current or we can say that it's the nominal current of the protected object. So if we are using a line, then we can use nominal current same as for the CT. If we have a in-zone power transformer, then our recommendation is that the end section 1 is set to 50% IR. And here we need to then consider if we have a tap changer in this power transformer as well. So that comes into picture here for the slope section 2, where we include the CT composite error and the tap changer position, and a relay measuring error, and also again a margin. For the end section 2 and slope section 2, we provide more stability to the protection in case of outside faults. So this is required then to have allow more differential current here in case of outside faults, where the measuring error will increase, and also due to partly saturated CTs, differential current will be measured. And then we have the high operate value here as well. And it operates regardless of harmonics due to inrush current, or and in case we are blocking the protection for other purposes. So it will always be on standby there. So let's then take a calculation example with numbers. So in this example, we have only a line that we are protecting, no in-zone transformer, and no tapped load. And as you remember, for the low operate value, we include tapped loads, charging currents for cables, relay errors, and a margin. So as we don't have any tapped load or in-zone transformers in this example, we only need to include the relay measuring error. And we need to include the measuring error for both end relays. And it's 2.5%. So that's why we have 2 times 2.5%. And then a 5% margin. So in this case, we will end up then with the minimum setting for low operate value, which is 10%. And since this is we are protecting only a cable, no in-zone transformer, we use the recommended settings 100% IR for end section 1. And why we are using 100% is because 100% here means the nominal current of the CT. And from this point onwards, when the load is increasing, also the CT measuring error will start to increase. For the slope section 2, we first look at, okay, what type of CTs do we have? Here we have a 300 to 1 amp CTs, 5P10. And here we are using the composite error of the CT, which is 5%. And we take this number for both end CETs. And on top of that, we include again also relay measuring error and also a margin. So this will result then in 20% for the slope section 2. For end section 2 and slope section 3, we have some setting recommendations. So here we don't calculate anything. It's more a recommendation to give as stable and sensitive protection in case of outside faults. So for end section 2, we have a recommendation of 500% IR, and for slope section 3, we have a recommendation of 150%. Let's then have a look at different applications where we can use line differential protection. So in this first example, we have a tapped load inside the protected zone. So normally this tapped load is a relatively small load. And as mentioned about the tapped load, it will be seen as differential current by the line differential protection. So we need to compensate for that to the low operate value. And what more we need to consider here is that this transformer of the tapped load might be protected by fuses, for example. So it means then that if we have a fault in this tapped load transformer or below, downstream of the tapped load, the line differential protection should not operate for those kinds of faults. Here we might need to increase the operate delay time for our line differential protection, so the fuses for this tapped load will blow before line differential protection will operate. And here we have an example of a in-zone power transformer. So it means that we are protecting both the line and the in-zone transformer. So for this, we also need to tell our line differential protection what type of winding types we have in the power transformer. What is good with line differential protection is that it doesn't matter which way the current flows in the protected line. So in this case, where we have a power generation from both ends, it might be that in some situation the power flows in one direction, and in other situation the power flows in the other direction. So since the line differential protection only looks at the differential current, so it doesn't matter what the power flow direction or the load level is. Line differential protection is also commonly used in this type of ring type network, especially if it's a closed ring here. Faults, for example, on one part of the line here, one part of the network here will not influence the other parts. So in that case, only the faulty part will be disconnected, and we still have power to all other feeders and loads that we have in our ring network. This can of course also be built with directional current protection. But that will be much complicated because you might need to consider some time coordination and also some blocking between the overcurrent relays. So it quickly gets quite complicated. And also in any case, line differential protection will operate faster than with the directional overcurrent approach. Here is another example where we are using this kind of a cross-blocking scheme for the earth fault protection. So what we are doing here is that we have applied line differential protection on this part of the line here. But we also, in case it's a compensated network, we also need to separately have a directional earth fault protection functions here. So for that, we can build this kind of a cross-blocking where, for example, if we have a fault here downstreams, this relay will detect that fault and send a blocking signal to the other relay, which means that the line differential protection will not, the earth fault protection for this line differential protection will be blocked for faults outside the protected zone. And this can be done by using the binary signal transfer function. So we are sending the blocking signals over the protection communication link. Okay, then a couple of words about CT recommendation for line differential protection. So this is a very important part of the protection because if you don't have proper CTs for the line differential protection, it might be that the CTs will saturate, and this will then result in a wrong operation, or that the operation will be delayed. So when calculating the CT requirements, it should always be done with respect of the maximum fault currents. So we need to calculate it both for inside faults and for outside faults. And with these fault currents, we can then calculate accuracy limit factor as a requirement for our CTs. And this must then be compared to the actual accuracy limit factor for the CTs that we are planning to use. So the goal here is that the actual accuracy limit factor for the CTs must be higher than the requirements. Now, here I have one example. What I would like to bring up here is that it's not only enough to look at the part of the line that we are protecting when defining the settings and the CT recommendations for line differential protection. We need to look at the overall picture. And for example, in this case here, when calculating the maximum short circuit current, we get different results depending on the network configuration. So for example, if we are feeding with only one transformer here, the maximum fault currents will be 10.4 kiloamps on this line. But if both transformers are connected, then we will have 19.1. Now, why is this important? Well, it's important when we set the high operate value for the differential protection, because it must then be set lower than the minimum short circuit current. So that's why you need to look at the whole picture here, and not only the line that you are protecting. So since there is quite a lot of calculations that you need to do, we have actually some Excel tool available, and this Excel tool can be found here on the ABB online support page. So this Excel tool, it will help you calculate the settings for the differential characteristic, and it will also help you check the CT requirements. So it will fulfill your application with its short circuit currents. And if you really would like to dig into the theory about the CT selection for line differential protection, here's another document describing that in detail. So if you want to look at this tool and this document, you can go into this web page. And the easiest way is to find this tool and document is by typing in the search field the answer ID number. So with that, we come to the final part, which is the summary. So what we have learned is that line differential protection, it operates only for faults inside the protected zone. So this means that it will give a selective and sensitive protection. And we always need to have a protection communication between the two line differential relays. And this can either be optical fiber or pilot wire, galvanic pilot wire. And we can use line differential for both cables and overhead lines. And we can use it also in case we have a tapped load or an in-zone transformer inside the protected zone. And it's important always to calculate the settings according to the application. So you need to look at what are we protecting? Are we protecting only a line, or does it include a tapped load or an in-zone transformer, and so on? And it's always a must to check the CT requirements for your application and check if your CTs will fulfill those requirements. This to have a sensitive and a selective protection. So thank you very much for attending this webinar. I hope you learned something new which you will find useful. Thank you very much.